in aviation, hypersonic flight has been a dream for the past 50 years. Now, supersonic flight is difficult, but hypersonic flight in regimes of Mach 5 and above, well, it adds an exponential level of complexity to the problem. I'm with Jeff Engel. He's the Chief Operating Officer of Reaction Systems, Inc. Jeff, at Reaction Systems, of course, you're working on components to make hypersonic flight a reality. Can you tell us a little bit about the difficulties? What is it about hypersonic regime, operating in that regime, that is so much more difficult than, say, a simple supersonic flight?
Yeah, so for our part of the hypersonic technology, we are developing a endothermic fuel system. So in hypersonic flight, the speed, as you fly faster and faster, the heat load on the aircraft around the airframe and specifically in the combustor gets so high that known materials can't survive in that environment, and so that you continually have to actively cool the combustor sections. And so we're developing a system, a fuel system to absorb that heat load from the combustor specifically, so that the final speed of the vehicle is faster.
Now, of course, in traditional engineering parlance, if you have a heat rejection problem, of course, we put a heat exchanger in, we put a working fluid, we circulate it, and we simply radiatively dissipate that heat someplace else in this case. Now, in hypersonic flight, you can't just hang a radiator into the airstream, can you?
No, that's exactly right. So through the heat exchanger that you're talking about that would cool the combustor section, it would just be, the combustor would actually be made of a heat exchanger, and fuel would be run through that. In historically slower speed flights, the fuel would be used to absorb that heat, and it might undergo some chemical reactions to absorb a little bit more heat, but there's a limit to that. You can't get a fuel too hot because you'll end up coking fuel paths, and if you coke the fuel path to the heat exchanger, then you lose fuel and the flight is over. So what we're doing is we're developing a new fuel and a fuel and a catalyst system that we will put inside the heat exchanger, and we will actually be able to absorb more heat than a traditional fuel.
Now, you're 3D printing these heat exchangers now. Is 3D printing an enabling technology for hypersonic flight, do you feel? Is this the way forward for heat exchangers?
I believe for us it is. We need a certain amount of catalyst inside the heat exchanger channels in order to undergo the chemical reaction to the extent we need it. And in order to get the amount of catalyst in there that we need at typical fuel flow rates that would fuel these engines, we need a lot more surface area than what you can do just through a straight serpentine path through a heat exchanger. And so with the additive manufacturing, we're able to do a lot on the inside surface of that to create more surface area, to create more contact with the fuel that would not be available for just traditional manufacturing techniques. So for us in this specific part of it, absolutely.
And what material are you making your parts out of?
These are being currently made out of Inconel 718.
So Faustin Tool, of course, is the firm that you contracted to make the parts in particular. Why did you choose them?
Well, so we had a phase 2 project with the Air Force that was coming to an end. We approached the Air Force and we said, we really want to take this technology to the next level, and we want to do a demonstration test. We want to test in a more relevant environment. And so we suggested that we manufacture a cooling panel to replace one of the sidewalls of their ground-based scramjet engine at Wright-Patterson Air Force Base. And they liked that idea, but they said, that'd be great, but we want this panel to be additive manufactured. We were able to take a small section of a panel that we had just thrown a design together. Faustin had printed it, and then we were able to get CT scans, X-rays of that mock-up panel section that we did, showing the internal geometry that we had designed. And I think it was a really key part of what gave the Air Force the confidence that we could do what we said we were going to do with these panels.
Jeff, what is it about Faustin that made you go with this particular firm to make your parts?
Faustin's fast response on our inquiries to what type of parts they could produce, as well as going over drawings with us to say, yeah, this is what we need to do, we need to change this, was one of the things that really attracted us to them. And the fact that they were local and that we could sit down and talk face to face with them was a big help. And how they've set up their additive manufacturing portion of their business. And for that, Heidi would most likely be able to talk with you about that.
Great, let's talk to Heidi. I'm with Heidi Hostetter. She's Vice President of Faustin. We're here in Arvada, Colorado, near Denver. Heidi, this is not a huge tool and die shop. However, you're a Tier 1 supplier to some of the aerospace industry's biggest firms, Lockheed Martin, Ball Aerospace, for example. How do you do it? How do you get a shop which is mid-size by standard sort of tool shop definitions, and yet you play in the big leagues?
I mean, really, Jim, that comes down to the people and the capital investment. Our guys are some of the best in the nation. What you'll find is that we have a real expertise in design for manufacturability, and our customers know that. They know if they come here, they'll get the quality they need, the service, and we're going to help them.
Now, it's in a mid-size shop like this, you wouldn't necessarily expect you to be adopting leading-edge technologies, but you have purchased an additive manufacturing capability through Concept Laser, which is not a prototyping machine in the front office. This thing is here on the shop floor. Tell me about that.
When we started to listen to voice of customer, Woodward, Ball Aerospace, Lockheed Martin, and a whole menagerie of others, small, medium, large, hands down, everyone said we would like somebody in this area to really learn the nuances of additive manufacturing.
I'm with Mike Muessel. He's manufacturing manager here at Faustin. Now, Mike, we've heard a little bit on sort of the 30,000 foot level, the overall view from Heidi about what it was like to bring additive manufacturing into this operation. Can you tell me in some more detail, tell me about the 3D printing setup that's here? This equipment is from Concept Laser. And tell me about it.
So we have a Concept Laser M2. It's a dual laser. So that means there's two laser. It's a powder bed machine. It takes a powder chamber, and we have a build chamber. And then the build chamber goes down and powder chamber goes up. Wiper comes across and disperses the powder, and then the laser fuses it in the build chamber. The machine that we have here, we are able to do reactive materials with it, so we can do your titaniums, your aluminums, that kind of thing. It has an actually separate side of the machine where you can change out in an inert environment if that's needed.
And of course, in the 5-axis world, holding the part is a critical problem in many cases. The complex parts, fixturing can be an issue, but still, usually you can sort of set the part up on a plinth, or you can hammer it into a Kurt vise, and you whittle it out and then just sort of knock off the base plate. It's a little more complex, I understand, with additive.
Yeah, so the thing about additive is you have to worry about, it's both a heat problem and also a geometry problem. So creating support structures that are right and that are going to work with the part are very important. If you mess up your support structure, it can cause the build to not build or overbuild, which then you have to stop and start over. But as far as setup, it's really actually pretty simple because you're putting it on a build plate and you're printing it. So I'd say more of the challenges are in the figuring out how to orient and support the part rather than an actual setup of the part.
Mike, the reaction systems part, it's a little unusual in that the interior of it is not just structure, it's actually the working surface of this part, so it really matters on the inside. And of course, this is a part that you really just couldn't be machined by any process. Tell me about what the build was like of making this very unusual part.
So with their part, it was a nice part size. It's something you can hold in your hand. So for the 10 by 10 build chamber that we have on the Concept dual laser out there, it fit very nicely in the chamber. Beyond that, we had support structures on the bottom of the part, so we were able to bandsaw the part off, and then we can put it in one of our CNC machines to be able to machine the part itself.
Dual lasers, what's the advantage of dual lasers? I imagine speed.
Yep, so with the dual laser machine on this particular part, if we did it with just a single laser, the runtime was about 5.5 hours. With a dual laser, we get it down to 3 hours and 40 minutes. So you can have both lasers working on the same part at the same time, increasing your speed, which is very nice.
Is there any single sort of piece of advice or best advice you could give to someone who's looking at bringing in additive technology into their operation?
Not really, just go for it. I mean, you have to get your feet wet at some point, so I think the more people we get involved with it, the better off we'll be.
Half a century after rocket-propelled X-15 test flights brought us into the world of hypersonics, it may now be possible to create air-breathing scramjet engines that will allow us to travel from America to Asia in 2 hours or less. Conventional machining won't get us there, but metal additive manufacturing clearly is the path to the future.